The third lecture in the atmosphere chapter is about the airspeed. Before we define the airspeed, let's first look at the ground speed. Ground speed is relative velocity between the aircraft and a fixed point on the ground. So basically, if we see an aircraft flying by our eyes and the speed, what we see, the aircraft is ground speed. Okay, then airspeed is a relative velocity between the aircraft and the moving air surrounding the aircraft. So if we have, for example, now we have wind in the same direction of the aircraft. So we have the v wind and the v ground. And then the airspeed is ground speed minus wind speed. And you may wonder what happens if the wind is against the aircraft. So in this scenario, the airspeed is ground speed plus wind speed. So we can write these two equations when the ground speed and the wind speed in the same direction, and also they are in the opposite direction. We can, if we write them in the vector form, so it looked like this. So the airspeed vector equals the ground speed vector minus the wind speed vector. So in this case, in a vector form, we can unify these two equations. And when we do the actual analysis, we need to distinguish the relation between the wind speed and the ground speed, if they are in the same direction or in the opposite directions. So we know the airspeed. Now the question is, how do we measure the airspeed? And on the right hand side, we can see two figures. One is about the pitot tube. We can see closer to the nose of the aircraft, we see the pitot tubes and also the static ports, pressure ports. Okay, the pitot tube measures total pressure because it's facing directly towards the flying direction, and the static port measures the static pressure. So now we can define the dynamic pressure. Actually, it has been discussed in the aerodynamic module. So the dynamic pressure is the difference between the total pressure and the static pressure. And also from the aerodynamics, we know the dynamic pressure equals half rho v square. V square is airspeed square. Okay, so then the airspeed equals square root 2 times the dynamic pressure divided by the density. That, remember, this is the density at the height, at the altitude where the aircraft is flying. If we have a more detailed look of the installation of the pitot tube and then the static ports. So this is how the channels are related, and also the airspeed meter, how it's connected to the static port and the pitot tube. And usually in aviation, we measure speed in knots. So 1 knot is 0.5144 meter per second. And so the airspeed indicated by the airspeed indicator, it's defined as the indicated airspeed, and the or IAS, VIAS, and you can see it's defined this way. In the square root, on the denominator, we have rho 0. That's the air density at the sea level. If we compare the airspeed definition and the definition of indicated airspeed, we see the differences in the denominator. And the indicated airspeed uses the sea level density, but the airspeed uses local density. That's the difference. Okay, so now we know the indicated airspeed is based on the sea level density. Just now we've defined the indicated airspeed, and in a denominator we make use of the air density at sea level. And also we have the true airspeed, which makes use of the density um, at the flight altitude. Okay, so now let's explore something new. And this is dynamic pressure and equals half rho VTAS square, true airspeed square. And now let's define the equivalent airspeed. So on the right hand side, it's half rho zero, and that's sea level density. And then we have VEAS squared, that's equivalent airspeed. So the equivalent airspeed equals square root half 2 times dynamic pressure divided by the sea level density. So equivalent airspeed is the airspeed at sea level condition, which gives the same dynamic pressure as that for given by the true airspeed. And you can see actually the indicated airspeed and equivalent airspeed share the same formula definition. Okay, so now let's find the relation between true airspeed and the equivalent airspeed. So that's the definition, the equivalent with the same amount of dynamic pressure. And then we can write VTAS equals square root rho 0 divided by rho times VEAS. Okay, so then we can do the inverse 1 over relative density times VEAS. Okay, so rho over the rho 0 is a relative density, and this we can find the relative density. We can find the number based on the ISA table.